for those of you who are not familiar with Mohamed, Kassem, he is the co-founder of ChipFoundry, and he's also a CEO of Native Chips AI. He has done a tremendous amount of work in the area of AI for chip design and chip design as a whole. And he's been very helpful for AI HDL and providing resources to us. And in parallel, ChipFoundry and of course, Native Chips AI. These are outstanding companies working in the area and trying to democratize access to chip design and manufacturing, which is really key for moving forward in this area and bringing new talent to chip design. So thank you for joining us again. Please go ahead. You can start anytime.
Well, thank you very much for the introduction. I appreciate you guys being here. Can you hear me well? Can you hear me?
Yes,
Good.
loud and clear.
Yeah, okay. Okay, so I'm going to share the screen and then let me know if you see it. Okay, so can we trust what AI builds? So the answer is no, by default. So that doesn't mean we can't ever, but it's by default. That's the right thing to do. It's better to be on the conservative side, and we'll talk about it. And then the AI and chip design is real. It's not a thing that's going to happen in the future. It's over. So it's done. It's been tried different. There's a lot of research. There's a lot of papers. There are a lot of companies that are actually using it in different ways. So it depends. Somebody's using AI somewhere. And some of the examples that are happening is that, some related primarily to Verilog and related to the architecture slash FTL development, which is actually very interesting because that's also one of the points where a lot of vulnerabilities can actually happen. So these are examples. Again, I encourage that everybody would look at these and see what they're, how they work. You can actually kind of clone them and actually see, get a feeling of what this actually does. But there are different frameworks that all of them still talk to the LLM, and they actually give you a feeling of what. Now, this is a short list. There's a lot more if you just type Verilog and actually LLMs or Verilog and AI. So the design process is a lengthy process. So it's kind of an upside down here, but the back end is optimization is something. The verification is a point. The RTL from natural language, that's something we use. Static timing and iteration around it. So this is actually where the system is being used. The different systems, AI, like Synopsys, DSO.ai, Cadence, Cerberus. So and the key part here is that that where AI is applied the most and why. So whether it's for the back end or the front end. So in general, there are many companies that are organizations, so including IDMs and companies and security-focused companies, and the research around the who's playing in the ecosystem, and so it's widely adopted, and you can tell even if you can even schools now, depending on which school you're in, and obviously the challenge that you're in right now is one of the examples of how things are done. Now, I wanted to cover this piece, which is the human versus co-pilot versus agentic. Some people, when they say, okay, I can work with Cloud Code or Codex, OpenAI Codex, and I can actually write something with it, but the word I exists, so I'm actually talking to it, and then there are so many times you will do something and you will keep repeating on a different problem, doing the same thought process, applying the same thought process. So that's how a co-pilot would help you, just repeating that process very quickly. But you have to repeat it again. So an agentic process, it's effectively a copy of your thought process for a given task or a given sub-project or a given problem. And you're saying, I'm going to have an agent. That agent is going to perform this task when I'm not paying attention. And the main thing is paying attention. So if I am paying attention and I'm waiting for a result, that's time on my side. If I'm not paying attention, this is actually the way I measure how humans are involved in general. So if you actually, nobody does this today, but we will be doing that. What's the clock time of how much time people spend in doing something, whether it's iterating on a timing report or architecture choices. Anytime it gonna goes to your head and it keeps getting repeated is an opportunity for automation. So these are just a high level, okay? And but once you have an automation, you can technically, you have no limit. That agent can actually run 100 times, running 100 simulations. It burns resources. You don't have to be putting guardrails around these things. The efficiency of actually productivity improvement in getting something like simple like a UART. Again, you can say it's a UART, but it's actually called a benchmark. There are so many ways that you can benchmark the general process, but for RTL writing and RTL verification, you can, with an agentic flow, you're sitting here, you can have a very solid UART. And why is that? Because the UART is a known device. It's not something that is, like if you're developing a machine learning accelerator with a specific algorithm that doesn't exist with a specific library, you won't find it on the cloud or the OpenAI wouldn't know about it. So it is, it is massive, and I can show some other things to do that. So now the people, when they select the task to actually say what AI is, I am working on something. I use AI to do the thing that I want to do or I'm doing more effectively. That's it. And there's a lot of, because I selected something, that selection maybe it's going to be better, but for me, but it's not. I could have selected something else that I don't know about that could have been better. The second one is the measurement. How much is my effort as a part of the overall development of a chip? So if I am talking about, if my effort is 30% of the chip and I make my effort 10x faster, okay, it doesn't make the whole chip 10x faster. Okay, so it's almost like you would have a multiplier factor per task, and that goes from it's not going to be below 1, probably would be always above 1, but in a large quantities, but it doesn't go to 0 because it doesn't make you unproductive if you do it right. So the knowledge of the expertise is still a very important piece, because the agents is effectively somebody who knows. Like if you're sitting in front of the cloud code and you're having a conversation back and forth, the only reason this is actually a conversation that makes sense to you and is that you're inputting things that you care about and you're asking about, and you're saying, okay, the UART or the I3C, I know certain things about it, and because I want to, I want to do certain things, I understand what the standard is, so I can say it. So I call it if you have if you think of the agent as a young engineer, and then you tell him to do something, and then they come back with a result, and then you look at it and say, okay, well, that's good or not, and then you feedback, and then you do this. Except the difference here is that you're actually, the learning process is encoded somewhere in either a database or the agent itself. When you do that, now that becomes an agent, because the knowledge, the effort that you went through to correct that young engineer, they they stick to it, and then sometimes they don't hear exactly what you're saying. So you need to make sure that you have the consistency checks and things like that. Yeah. So and then and actually the last one here is about the evaluation models, and in general, it's something that you have to. You can say I am accurate X 99%, or you can be good at something, but subjectively, people are they're actually feeling about things. However, there are quantifiable, obviously, benchmarks that you can do things about with, and we need to stick to that. So we need to. One important thing is that LLM doesn't know everything. It doesn't. Think about the LLM as the only data that the LLM has, any public data. And the public data is typically about 5 to maybe 10% of the available digital data. So, and except for leakage. So you're going to find any theoretical knowledge, any published knowledge, it's already there. So assume that the model knows all the papers about everything. However, if there's subject are mentioned once in the entire 10 years of the internet, then it's not going to be, you're probably going to get a hit or miss, unless there is a way to have the model derive some of this. But think about the code online, think about the academic paper, books and data sheets, blogs and exchanges. That's what it knows. On the other side, like if you want to experiment that, go find that TSMC, pick a process, like the 3 nanometer, for example, and ask ChatGPT, give me the transistor model parameters for this. It will not give you that. And sometimes, actually, I forgot what happened. I think one of them told me this is a very specific piece of information. I don't think I have any public knowledge with. But if you try to ask a serious, deeply, secretive thing, not to ask it to estimate the VT, for example. It doesn't know the rules. It doesn't know unless you're actually sharing. Sometimes it depends on how I actually, in this part here, the negative knowledge, it exists. But again, if you push back on something, it can actually listen to you and it says, oh, you're right. So you got to be careful with these things. And then, of course, there's a training period where it doesn't go beyond it. So just, the difference, the LLM is not equivalent to the agentic flow. An LLM will take the text in, text out, and they cannot run code, cannot run tools, cannot do anything. The agent is basically, if you think about yourself, you're getting a code that like Claude generated, and you take that code and run it on a computer, and then take the results and feed it back to Claude. This process is agentic in a sense. If you remove yourself out of it, becomes a completely agentic process where they can run the tool. And very good example of that is Cursor. You can run things and it will find issues and it will correct for them. We do the same in chip design. Okay? But it's important to know what's, where are we coming from in terms of LLMs, and you know what it doesn't know. Okay? So the security piece is actually a little worse because it's a subset of the entire data set. So the general population of the information is, it's great, but it's still a smaller data set. There's a lot of, you can count the number of places where security is being discussed or forums compared to general software, for example. Then the other aspect is that is you knowing, if you know something about security and actually how to detect it, you start actually talking directly. And then with the agents, where you're basically using the inference from like what you're doing with the ChatGPT or Claude the agent itself would contain the information that you recorded in it or wrote it. So these are the type of knowledge about the topic like security. The things, everything I mentioned is kind of staticky, unless, just keep in mind that if someone publishes a new paper, one paper on a new architecture, it does not doesn't have enough population to go swing and change the behavior of the model. So there is a lot of static data in terms of what the model used to learn, and unless they're actually they're moving year by year, but theoretically, you can be, if you think about it, I would think the entire internet since the inception of the internet until today. I think that if that's not happening today, it will happen. So now I'm talking in general on the entire chip design process, but I'll get into specific spots where the things going to happen related to the using the AI to in a design step, in a certain design step. So if you kind of ask Claude something about what are the threat models that I have, you may actually not get a right answer. You will get a lot of good stuff, but it may not be complete. And if it's complete, it may be less specific. But you won't be surprised that it will give you something, and it will give you RTL, but the RTL will function 100% correctly without any regard for the security level. And the RTL, if you go to the RTL after the architecture, it's interesting. This is what I didn't know about it until recently. The white fonting, where if you give the AI a data sheet, and then that data sheet has instructions in white written on the paper, and it says ignore the following. That's literally a Trojan injection. So you could have a document that will have instructions to do certain things that are harmful. So as an example, of course, other than hallucination and all these things. So the verification is an interesting one, because if you designed RTL with a model, you can't just go to verify it with the same correlated system. So we do this in the design today is by having independent teams for design and verification, and you do this in order to decorrelate it. You do it with and I'm going to actually go very quickly over them. So we talked about the prompt injection, and this is the part about the white text. So and then now that you know that's possible, you need to know what is in the prompt. What exactly am I putting into the prompt and confirming it, so that this is doable. So it's not something. This is an example of something like this. Okay. And obviously hardware backdoors, and so when sometimes it's easy actually to say I'm going to take that data sheet and then do something with it, but here you go. So again, the training data itself. So it's not. It doesn't. The quality data that you believe is good to control data for training a system may not be available in the right quality to train that model. So you don't know. You would know. You would know that it's trained on the internet in general, but you wouldn't know exactly what the like, for example, a second order effect, like having simulation data, for example. It's not the LLMs are not simulating that. So any calculations around inside that, you don't know, what's happening. So this is the one about hallucination, and it is kind of the same AES functionally. It's going to stick, and the difference is that the key scheduling is so much more robust on the right hand side. But if you actually just do verification on the function, you have a problem. So there's a need for the right mechanisms to detect these things. This is the verification piece, where if you have a model to do the verification, do the design, and then you use the same model, you actually the same. That's the typical blind spot thing. So you could use two different models in a process, and it's actually interesting. You could do more than two actually. So and then I'm not a security expert, but some of these things are very, when I brought them here, because they're very interesting, about how it tell you can ask AI to do a lot of things, and it will make it so much easier for you to inject something, to hack something, or poison, or inject a Trojan. And a couple of years ago, we ran a competition where design with AI. Actually, it was a different guy. It was in university, in NYU. I think there was a CWE related competition that actually it was generate Trojans using AI, which actually it became very, very interesting, because the people, even the judges of this competition, were so surprised what could happen. So, and then I can go, this is a subset, or a kind of a list that you can go to with pointers and actually start looking if you're not familiar with the topic. And that's actually what I did myself. And then the models themselves, to start, there's something called data scheming, for example, where the model is actually adapting to a type of test. So and this was an Anthropic story, is that the model will show less harm in certain activities to pass the safety test so that it can be released. So this is actually, it's called scheming. So imagine there are some things that if you keep testing certain things, and there is an opportunity that the model would extract this data or learn from it, you're going to end up mutation effect. So now there's the physical design, there's the software. So if you look at the entire vulnerability of a system, it has the software piece, it has the hardware piece. The software bugs can be resolved, but if you have a vulnerability in the hardware and it's already deployed in, I don't know, a million places, it's not recoverable easily. That said, so we have a problem now, and then so if we come back and say, okay, let's use AI to do this, so to actually detect the Trojans, and it's kind of interesting, because you're saying I don't believe in AI, and then you're using AI to check on AI. In my opinion, generally speaking, decorrelation about the checker is always a checks and balances system, and you can build a system that is uncorrelated. Like, for example, sometimes I give a prompt and I give it to 10 models, the same prompt, and then you come back, and then there's a process to refine that and come back with an answer that has the most a complete set of information, and anything that is not apparent in any one in all of the model, all of the answers, it would be removed. So there are ways of doing these things in such a way that unless the AI models at some point they collaborate together and say, okay, we're gonna go screw the humanity by doing by making them everything think that they're correlated, but they're correlated. So formal verification, that's math. You can actually do something and check. At the end of the day, you get into the hard as you get closer to the physics, actually including formal verification is something, but also having like spice simulation, or the closer you go down to the physics, the more likely that you're able to verify it 100%. Now, the pre-silicon, so side channel analysis, there are companies that do that now. So that's you do it so you can detect something before and you change the code. So to the extent that people would do test chips, and then they run the test chips in a real lab, and then they come back and recorrect or iterate on their software to confirm or improve that the ability to detect side channel attack vulnerabilities. So you can build agents, and these agents, again, they use the LLMs, but the agents are typically the doubtful entity. So if you think about again, think of yourself as the agent is a representation of you, and if the agent knows what you know, they will be able to judge certain data in a different way, certain responses, and they can refine the response. So again, it stays, there are still blind spots because I know what I know and I don't know what I don't know. I mean, the whole thing, so simple things that I don't know. So you can encode as much as you can, and then you still have blind spots. But, you can also do this, design basically for security. And then we, like, for example, in our company, Native Chips, we have the gates, and these gates between the design steps, we confirm the same gates that we would confirm typically in a design without AI. So if I have an RTL implementation, and how do we do it today? There is a verification and a verification process, and this verification process is done by trusted people, and the trusted people say it's passed. You can't do it. At the end of the day, you're gonna have to stop at somebody that says it passed, and that's you, you take that and make it enforceable, so it becomes a gating process to avoid. Now, I'm talking. This is actually kind of fun. I'm talking to you. I don't know much about security. I know, I know enough to be dangerous about security. So, but I actually, because I'm talking, and I founded three companies, and that everything I said here has to be right. So no, okay. So you have to check my facts, okay? Because that deck itself was generated with AI, but I was the agent. So I went back and forth to ask questions to make the points that I want to make, and some things didn't make sense, so I had to go back. Okay, so check my claims. Sometimes anything I say again, just because it's I said it with authority. The LLMs tend to do that. They think they're always right. Okay, but if you push back, it's just like, oh, I'm sorry, and you've seen it already. So, the one of the tricks that actually I saw somewhere and I started using it is about how to say to, and there's a specific prompt that you can put in the instructions, is that I am the following person, and I question or all the answers that come my way, and I always check the sources that the LLM would give me answers based on, and you put that in an instruction, and it becomes a process where anytime the LLM or the answer comes out, it comes out with sources, and then you check the sources. So you start doing some, and then so just that fact that you say I am a critical person. I pay attention to details, and I want you to give me a source for everything you say. You're actually starting to clean up the process by doing that. This is, the there are things already. As I said, this is before AI, security issues existed. Okay, but if you think about it, in summary, the threat models, the decorrelation of the verification. Now, there's one more thing that is mentioned here. Number 6 is the provenance of the IP. If you get an IP that has a hole in it and it's black box to you, and you inject it into your chip, you got it as well. So it may or may not be accessible, but there's a lot of people that actually think about these things really well. And you always have to have the concept of a red team, blue team. As soon things are going to go wrong, and you have people, their job is to dig into how to break it. So this is the summary of what I just saying earlier. I drafted the requirements for the deck, okay, and the Claude drafted slides content based on my requirements, okay, and then I started verifying it. I learned in the process, because I develop chips, and we develop it with AI. And although I didn't cover it much here in a way, but it is that's how I was able to do this. And then I believe I checked the sources, so I did a good job in it. But let's see. So I think this is it. This is just a carry home points, in terms of, their AI now is designing chips, with agents. We're doing it some autonomously and some not. And then security can be uh, prioritized. And if you do that, it, it will at least reduce the risk of something like this happening. Um, um, there are blind spots in the design process. Just need to um, the we need to know what the LLM actually knows and try to think of this process all the time. So, and then there is this is kind of an illusion about the can build versus guarantee. So, for example, one of the challenges we have is that if I write a prompt to design a certain chip and I need to do it, if you do that 50 times, do you get the same exact answer? What do you get? That's another thing, because the model response is probabilistic. So you're going to have to, so there's a difference between I can and then when I actually guaranteed it works. And these, especially when you have something like chips that have lives on the line. Thank you.
Thank you so much, Mohammed. That was a very thought-provoking presentation. I really enjoyed the conversation you had around, security and AI and how to think about these challenges, right, that you pointed out. And, my lab and my team has been working on some of these challenges, including like Trojan and AI. We actually yesterday got news of acceptance of our paper on the same exact topic of hardware Trojans within transformer models. And I want to open the floor for others to ask questions. So feel free to put your questions in the chat, and I'll read it out. And as our folks are thinking about questions that they have, let me start with this. So your last point and your last slide, we're talking about guarantees, and one of the guarantees that I'm thinking about is how do we how are we going to be able to guarantee security? Of course, it's really difficult without a unified metric to come and say, yeah, this hardware is secure. But then what do we mean? What do we mean by that? What does security in that context mean? Do you want to add something to that?
Well, again, if you think about, and I actually don't know what the answer is. We know what we know.
Yes.
We think we know. Anything we know is coming based on our conditioning of previous knowledge.
Mhm.
So there will be blind spots. There are people that are inquisitive about finding these blind spots. The difference here is that you can use AI to scale and more aggressively find these things. Like if you're checking something yourself with a code, with a piece of software, you can actually, the agent will help you do it, a million times in different ways. Um, the uh, and the second thing is, if you put that on the other side, someone with low knowledge of how to hack the system, AI we're going to make it, or we can make it much simpler. So puts another problem in terms of uh, guaranteeing. So I don't think we learn, and it seems like, for example, the Trust Hub, University of Florida. So there, you're learning, you're accumulating things, and then you try to predict certain things. But I don't know if there is a guarantee. So there's a guarantee to to do that. I met the requirements that I know I need. Okay, but cars still fail and people die. Okay, they can't.
Absolutely. Yeah.
So, so
I agree
but
with you 100%. Yes.
and then in general, if you have a process, it's at least a good thing. If you don't have it at all, then you're wide open for everything.
I agree. I agree 100% with all the points you made. The way I think about it, there's no way you can guarantee any form of security, right? Because as you said, you know what you know, and there's so many different vulnerabilities or threats that you might not be aware of, or there are like nuances in there, right? So there are like emerging threats and evolving threats.
Mhm.
So it's really a landscape that also evolves with AI. So AI is, of course, is used for design and security, but also attackers are using it as well. And we see the new news about the Claude Mythos model, right? That is
Mhm.
making waves. So, going back to what, again, what you said, and you had it on a slide, trust but verify, right? So, going back to your point about don't just trust the speaker because they're kind of like an authority figure and whatever they say, it doesn't mean that it's true. But, I've personally had a lot of experience and where you give a prompt, you get a response, and the response is 100% like wrong. And
Mhm. Yep.
with such a level of confidence that if you don't know anything about it, you'll be like, okay, yeah, makes sense. So it kind of goes uh, along the line of what you said about
Yeah.
different prompts would give you different designs.
Yeah, exactly. And then there are some interesting things. I don't trust it in general with numbers. So if
Mhm.
it gives me,
Yes.
like if you go ask the exact mask price for 22 nanometer, I know, you're not going to get it right. It's an estimate. And sometimes it's 10 times so numbers in general that come out of the system, the good thing about it is it's verifiable. If you either can verify it or not,
Right.
and
Yes.
easily. So
Yeah, so that's definitely on my mind. So I've been thinking about, okay, so if different prompts give you different outcome, then the prompt engineering becomes key here, of how would you go about prompting AI so that you are minimizing those hallucinations or those issues that could come up.
so I found a way to get you calibrated on what a good prompt should be like.
Hmm.
I want you to describe what this is without telling me it's a bottle.
It's cylinder
Good.
shape. Yeah, cylinder shape made of plastic, with a label on it with a plastic um, closer,
That's the point. So you do the more details. If you actually do that with the ChatGPT, if you can actually say, give me without telling it me it's a bottle. Here's the
Mhm.
prompt, and you generate a prompt that I can use with ChatGPT. And
Mhm.
you take that prompt, shove it into ChatGPT, you get a picture of a bottle, very nicely done. Okay. So my recommendation is that test, and it was done actually. I learned it accidentally. I was watching somebody who was teaching kids how to describe things without saying they were like blocks, but they didn't have a name really. But and then it came to me is like the way when you describe something, if you describe it in English, this is something we're not used to. By the way,
Mhm.
in general, we're not used to doing that, and so you're gonna have to think this way. How do I describe it to somebody who doesn't understand it? Okay.
Right.
The more you do that, the better response you get.
It's a great way of thinking, actually. It kind of puts things into perspective for our participants as well. That maybe the prompt is not the prompt that gives you the best answer is not the most straightforward, like give me a bottle. You have to add a lot of details and descriptions that would help you get to the better
And that
response.
and so consistency in the response as well. So if
Yes.
you just say a bottle, it's going to give you different bottles, different
Yeah.
types, different. But if you start saying very specific,
Yes.
more consistency will happen.
Wonderful. Thank you. I see a couple questions in the chat I will just read over. So, from a hardware security standpoint, how could AI be exploited to embed stealthy hardware Trojans? And what are the emerging research trends addressing this threat? I think you pointed out some of those in your slide
Yeah.
deck.
So here you just go open one of your favorite LLMs, ChatGPT, and say generate the following. Uh, generate, give me an example, two examples of one that is secure and one that has vulnerabilities. Of course, it can fool you in that, but for a second, if assuming that it's actually telling you the right thing, you will see the difference between the code, even though it's functionally correct. And you can simulate that and confirm that this thing does that. Call it, whatever it is that has the vulnerability. And then there's the security, by the way, in the block level and architecture level, and so it's a complex issue. So there is a lot of research actually. um, a lot of research, and you're in the right place right now. If you're in this, with Professor Sahil. Uh, you're in the medium of research. This is the where with some of this work is actually the leading work is happening here. So it is. Try also another example. Um, Take some encryption IP, pick it from GitHub, and then ask Claude to modify it to generate in English a backdoor. So again, if you can describe it in even more details, you're just gonna do it. It's not gonna stop. Okay. So these are things that you can actually do yourself because because there's enough research that actually the model can give you something and then you can verify it.
Wonderful. And a follow-up question about that is, do you see opportunities to combine AI approaches with statistical or cryptographic techniques such as TRNG, to random number generators, or hashing for more robust hardware Trojan detection?
Well, I can't say I understand the question for sure. Basically, the question says, can you combine the AI-based approach as well as some the mathematical or some hard approaches to have more robust uh,
Detection.
Trojan detection? And the question is detection where? Is it pre-design, like pre-tape out, like you're doing it in the architecture level or in the code? In my opinion, is that if I understand the question correctly, math doesn't lie. You have, and especially if it's around physics, like so if you have the agentic AI and you have some sort of a physics-based, and I don't know what would it that be in a specific in the cryptography, but I think you can. The question is, I don't know what exactly you do. As I just said, I'm not security expert, but you can have a combination of AIs and a combination of a hybrid approach of AI and a traditional approach, or you just choose for certain things. I'm just going to do what I know and just let AI start. Maybe let AI help me attack it.
Mhm. It's wonderful. Yeah, yeah. I mean, I 100% agree. Definitely, uh, it's good to pair AI with some sort of known methods that traditionally been used and confirmed that with good extent can detect Trojans. And these approaches are not necessarily new. But of course, AI can help accelerate things, right? Cut down your time of detection potentially, help you find these vulnerabilities faster. I believe that's going to be the key moving on, where we're cutting down the time for designing and manufacturing a chip from months to um, for design from months to weeks, and then
Weeks.
that's going to be a key
Yes.
accelerator, right?
Yeah, absolutely.
Any other questions from any of our audience? And of course, this recording will be available after this webinar concludes.
Well, thank you very much for having me, and
Of course.
I look forward to actually contributing more and learning more, most importantly.
Of course. Thank you so much for presenting for our audience. And, again, thank you for sponsoring AI Harvard Design League. And your outstanding support has been a big push for us and big motivation point.
Thank
So
you.
thank you.
Thanks
Thank
to
you for
you
that,
as well. You're welcome. Bye-bye.
of course. Bye, Mohammed. All right. Thanks, everybody, for being with us for this webinar. If you have questions about generally Design Phase 4, feel free to reach out to us. We have the award ceremony announcement that is released. Make sure you RSVP. There's going to be for those of you who are attending virtually or you're not in the United States, you can participate virtually and via Zoom. If you're interested, if you're UOA student, you're definitely encouraged you to participate in person. or if you're in the US and you plan to travel to Tucson around that time, we'll be happy to host you in person as well. Thanks again for participating in this webinar, and let us know if you have any questions. If no questions, then I think we can conclude this session. Thanks again, everybody, for joining us, and wishing you a great weekend ahead. And good luck with your final submissions. We look forward to receiving your submission and seeing you at the award ceremony. Thank you, everybody.